Hi everyone, I am Hằng. In this video, I will talk about the second law of thermodynamics. So I keep continuing with from the previous video. In this video, I will talk about the entropy and the left thing. Okay, so I immediately move to the entropy. So I remind a bit. Previous video, I talk about this sum already. Now we move to the entropy. Is the next slide. So I rewrite this information from previous video. The sign equal when we have a reversible process, and smaller than 0 when we have irreversible process. Now we consider a closed cycle like this is irreversible cycle. So now we apply this formula. I rewrite this one. So now I divide this process in two processes from 1A2 and then the second process 2B1 like this. So what do we do next? Here I move this term to the other side of the equation. So I have this one. Now if I don't want to have a minus here, so instead of 2B1 I change to 1B2. So here I change the minus to plus like this. So now you see if we have a reversible process, so whether you go by 1A2 or you go by 2B1, you have the same, the change of heat over temperature is the same. So we call this quantity is change of internal change of entropy. What is entropy? As here is state variable. It represents the state in the system. So the change of entropy is the change of the states in the system. Okay. Next, what do we have here? Remember, delta S is the change of entropy, and entropy represents for the change of the state, and the state depends on the each position of the particles in the system. So when the particle move here and there, so you have many states in the system. So how does why the particle move? How to make the particle move in the system? You just apply, give the system heat, so that heat will make the particles whether it moves quickly or decrease the speed of the particle. That means when you change the position of the particle, so you change the state of the system. So conclusion, entropy represent for the chaos of the system. Next, so we have a formula for the entropy like this. Okay, the next example, I suppose that I have a irreversible process. Also this process also closed but include irreversible process. So how do I calculate the entropy? How do I consider this information to this situation? So I also calculate this one, but because it includes irreversible process, so here I have to pick up the size smaller than 0. Okay, so I divide this one, the closed cycle, in two process. The first one from 1A2 like this, the second one 2B1. Actually 2B1 is a reversible process and 1A2 is irreversible process. From this equation, I move this term to the other side of the equation. So I have a minus here. If I don't want to see the minus, I change the direction. Instead of 2B1, now I rewrite it 1B2. So I neglect the sign minus. Actually, this one represent for reversible process. So here will be the delta S, or the change of entropy like this. So here I will write delta S. So you will see delta S is greater than this one, greater than this one. So conclusion, if the process is reversible, so I have a delta S, I mean the change of entropy here. If the process is irreversible, so the entropy always the entropy is always greater than this one. Okay, so that one is also the principle of increasing entropy. Next, what do I have? I have some conclusion for entropy. So you see, entropy just depends on the initial and the final position, state, actually state only. So the way it goes, it doesn't depends on the ways that the path that the process goes. Okay. Next, now we calculate the principle of increase of entropy. I said before already. So entropy of a unreversible process always greater than zero. Entropy of this one is irreversible, okay, and this one reversible process equals zero, and you never have any process which entropy is smaller than zero. Okay, now we calculate the change of entropy of an ideal gas. So how do we calculate the change in entropy? How do we calculate it? So you get the change of heat divided by the absolute temperature of the system. So if you want to calculate the change of entropy, you have to calculate the change of heat of that system, the heat that the system received during that process. So if you want to calculate the heat, you have to apply the first law of thermodynamics like this. From here, you get the heat equal du minus pdv, plus pdv. So when you keep looking down, so it's a bit mathy, apply math to this. So here you get, you know that the change of internal energy, actually the change of temperature, so you rewrite it. You rewrite formula for du. You remember that we have the equation for ideal gas, PV equal nRT. So if you have a PdV, that means you have a nRDT, for example, like that. So you rewrite this one, and this term actually you rewrite by this way based on the one I just tell you, and T here you have a T at the numerator, and you have a T in the denominator, and then you cancel them out, so you have this formula, and then you take you do the integration here and here. So you have here you have a delta, the change of entropy, the change in entropy. Sorry, I always say the change of entropy, but actually it is the change in entropy. So here you have the change in entropy, and when you do the integration in this side of the equation, so you have a dt over t, you have a dv over v. Actually this one, the result is the natural log of t and natural log of v. You have this function. Next, if you want, you know that if T2 over T1, so you can rewrite it through the P and V, because the PV equal nRT. So from that, you get the, instead of T, you write through P and V, and here you have a log of P2 over P1 times to V2 over V1. So you rewrite it by this way, rewrite in kind of a sum. So now you neglect it, or you make it shorten it like this way. So this one is the formula for entropy in of an ideal gas. And here is in details. If you have isothermal process, you calculate the entropy by this formula. Remember, you have a heat in the video about the first law of thermodynamics, and because isothermal process, so the temperature always constant, so you get the heat divided by temperature like this. And for isovolumetric or isobaric, So you get the heat divided by the temperature, you do the same. But for the adiabatic process, so it's a good news because the adiabatic process, so the heat equals 0, and you calculate the change in entropy through the heat. So because the heat equals 0, so the change in entropy equals 0. See, that's all for this video. So you try to remember the entropy of this one, okay, for processes to apply to the exercise. So the main point in the second law of thermodynamics is the change in entropy. Okay, thank you for listening.